Okay, so today we'll start our third lesson already, and we're going to deal with two topics with Python in general and a little bit of linear algebra. We're going to do it in an extremely basic and informal way. And basically, the reason we'll be doing it is to sort of bridge gaps of some of the students here, because I understand that at least a few are not familiar at all with linear algebra. Others are not very familiar with Python. So let's try to bridge those gaps. So first of all, Python is, I would cautiously say, is the language of AI. Almost everything is done with this language. Um, it's pretty efficient. There are a lot of innovations in it. Some of them are even daily. I'll show you one today. And I suggest that we start with a very simple example. We'll try to solve a problem with Python. And the problem we'll solve is a very interesting one. And with your permission, let me just do a screen share. Just let me know if you see my iPad. Okay, I think we all see it. Very good. So we'll solve a very interesting and ancient problem. Actually, I was shown this problem about 50 years ago when I was 16. And this is how I fell in love with the computer science. And actually, this problem made me make the decision to be a programmer. So the problem is very interesting. We want to calculate pi, but in a very strange and indirect way. So you can also see here a drawing of a circle with a radius 1. And I think you would all agree with me that the surface, sorry, the area of this circle is simply pi. Oh, I think we have, sorry, we got disconnected. I guess we'll have to do it again. Oh, okay. So basically, we all agree that since the radius is 1 and the area of the circle is pi r square, then pi should be the area of the circle. So just, to be very simple about it, imagine that we drew a circle with a radius of 1 meter, and then took scissors and went all around the circle. Then the area of the circle, of 1 meter circle, would be pi. But let's make it more interesting now, and let's look at the square here on the top right. So you all agree with me that the area of the square is simply 1. And the area of the quarter of a circle is, of course, pi over 4. Which means that pi actually equals the area of the quarter of the circle over the area of the circle, just times 4. Do we all agree? Okay. So now let's be a little gamey and sporty. And imagine that we start shooting darts at the square, but only at the square, okay? Hundreds and thousands of darts we're just throwing on the square. I think you will all agree that if these darts are really going in random within the square, then pi will actually be able to 4 times the number of darts that are in the quarter circle. over the total, sorry. So if we threw, let's say, 100,000 darts within the square, and then we only counted the one that were in this area, in the quarter circle, we'll call these, let's do it simply. Let's call it, sorry, 4 times n in. So this is the number of darts that went in the quarter circle over n total. So basically, if we're able to shoot, let's say, 100,000 darts within the square, and then count only the ones that fell within the quarter circle and divide them and multiply by 4, we should get pi. It's a very indirect way of doing it, but it's a very popular way of doing things in physics, in biology. And let's program it. But before we do that, there's an interesting question. Let's start thinking like programmers. So in order to throw a dart, we need to have a sample x between 0 and 1 and a y between 0 and 1, because we want everything to be in the square. But the question is, how do I know whether the dart is in the circle or not? And the answer, of course, is very simple. Let's say we have a point x here, okay? Then the distance of x from 0, 0 is, of course, the square root of x squared and y squared. So x and y are two random numbers, right? Between 0 and 1. R will be, of course, also a random number, but it's the square of x squared. It's the square root of x squared and y squared. Now, all we need to make sure is that R is smaller than 1. So if this is smaller than 1, smaller or equal to 1, then we are okay. So what we will actually do is just create a loop. The loop will run as long as and the number of times that we want to throw the darts. So, if we throw 10 times, obviously the calculation will not be very good, but if we throw 1,000,000 times, it will probably be better. And all we need to do is simply count the number of darts that fell inside, divide it with the total number, multiply by 4, and if all goes well, we should get pi. Do we have any questions so far? Perfect. So let's now start programming. I sent you all a link to something which is called Google Colab. Google Colab is the best way to do Python programming. It's the simplest way because you don't need to install anything. All you need to do is just go to the link I sent you in the chat, and we'll start programming in a minute. Just a very important comment. If you really want to do programming, I would suggest to download a product called Anaconda. And Anaconda is a Python package, but it includes something which is called Jupyter Notebook. And Jupyter Notebook works on the same format as Google Colab, but it's much more easier to work with it because it's a client, it's running on your computer, it's much faster. So, if you don't want to deal with logistics, just go to Google Colab. It's a website, you don't have to install anything, everything is simple. If you want to be a little bit more professional and do some more complicated things faster, I would consider moving to Jupyter Notebook, which, as I said, is simply a part of Anaconda. So let's see what it's like to write code in Python with Google Colab. Okay. So first of all, the way in general, both Google Colab and Jupyter Notebook work with something which is called notebooks. Notebooks are cells, are a combination of cells, and each cell in a way is a unit. So here I started with a very simple cell. A equals 5, W equals hello, and C is a matrix. and I asked to print C, and I got this. Let's just add another cell. Let's say here, print
You're not
W.
sharing your screen.
I'm
Please share
sorry?
the screen.
Oh, I'm sorry. Okay. Okay. Do you see my screen now?
Yes.
Okay. So, this is the first cell. A equals 5, W equals hello. So A is a numerical number, W is what we call a string, and C is a matrix. And here I told it print C, so it printed this. What do you think we'll get with print W plus W? We'll get simply hello, hello, right? We're just connecting them together. So to run a cell, we can just click on this arrow here. And as you see, we got hello, hello. There's a nicer trick when you start working with cells, which I like very much, is you just click on the cell, you make it active, and then you click on Shift Return. And that makes it much quicker. So what you saw here is a very simple example of writing code with Python on Colab. So everyone that was able to do that is already a Python programmer. There is an amazing innovation which came lately to Google Colab, and I'll show it in a minute. So you see here, I opened a new cell. When you want to open a new cell, you just go to plus code. So I just opened a new cell. And what I found, and this is relatively new, that there's a button that says generate with AI. In other words, you don't even have to write code. You can just say, I don't know, write. Oh, sorry, I didn't click on generate, sorry. So I click on generate and write a simple loop which prints the numbers 1 to 10. Okay. For some reason, oh yeah, okay. So it did write something. It didn't print for some reason. I would say that in terms of AI, it's still not as powerful as going to either ChatGPT or Grok. But I also use it from time to time when I want to do something very quickly. Instead of going to ChatGPT, I just use the generate and write a code. Okay, so let's do something which is a little bit more serious. Excuse me. Okay. So this is a notebook that I prepared before we do the Monte Carlo thing. And what I did is simply ask it to write a function that writes the Fibonacci numbers. So what you see here is this is how we define a function in Python. I even called it BIU in order to make it our function, so no one else uses it. And I also asked it to do the commentation. So we have the commentations there. And what we see here, let's look for the function itself. Okay. Here we get an input from the user because I asked it to have the user input a number. And of course, here you see the very simple Fibonacci. Let's run it. It asked me for a number. So let's give it 11. And I got a print, enter a positive integer. That's what I did. It was 11. The Fibonacci sequence up to term 11 is blah, blah, blah. Okay. So let's go to the next cell. Here I asked it also to plot, and it gave a plot of the Fibonacci series, and I also asked it to do a linear graph just to make sure that it to see what it looks like, to see how far it is from linearity with small numbers. And of course, you know, everything is really, really important. Let's quickly go through the main things. So import, what we did here, Python has libraries, tons of libraries. This is a simple, very important library, which is called matplotlib, and it's used for plotting. And the reason it was important because I asked it to plot. By the way, this is the heart of the Fibonacci, okay? A plus B שווה B plus AP. And this is the plotting. Now, something which is very important for you guys that are not programmers. I wouldn't go very deep into the plotting business in Python. It's very complicated. If you're not a programmer and if you just want to use it as a scientist or a physicist, just disregard it. You know, if you want to go deeper, you can go to ChatGPT and ask about each command, but why bother? All you need to understand that this area does the plotting. If you want to play with it, you can always play with parameters, and this is what we got. Okay. So now let's go to the more interesting part, and that is the Monte Carlo pi calculation that we just discussed. So what you see here is the code that I got for simply asking it, give me do the Monte Carlo pi calculation. So first of all, it imported a random library because it will need to do some random numbers. It also imported math because it will need to use things like square root. It's a math, something taken from the math library, and of course the plotting. And this is the function, it's called def, it's called estimate pi. In Python, when you define a function, you just add def. So it's called estimated pi, and it gets only one number as parameter, of course, which is the number of shots, right? This is the number of times I throw the dart. So we don't have to go very deeply into things here, but let's try to understand. First of all, the most important thing is the loop, right? Because we're going to loop on every dart throwing and calculate the distance from the origin. So this is where it's all happening. You see, we're doing X random and Y random. Here we sort of get the two random numbers. Hey, look at that. Here we get the distance. So it's square root of x squared plus y squared. And, sorry, in order to understand whether it's going inside or not, we just need to compare it to 1, okay? So points in distance, we're just comparing distance to 1. And if everything is okay, we simply append it, add it, sorry. And what you get here is a very nice graph, which is showing the darts. The darts in red are the ones that did not make it into the circle. And what you saw here is we just did 100 darts, 100 points. And pi came pretty ugly, 3.4, right? And the error is 10%. But I then asked it to do some more calculations. So here we already have 1,000, okay? And now we have 1% mistake. Error of 1%, 1.3, sorry, 1.32%. Okay, and here pi was 3.1. And I think we did another calculation for 10,000. And now we have 0.27 error. And for 100,000, we get a small error as well. And look how nice it is. Now the beauty, everything you see here was done with a one-line prompt. Now, that's even crazy. That's 1,000,000. And here we have almost 0.1% error. So we practically got pi. Now, obviously, that's not a clever way to calculate pi, we all know. But what I thought, and perhaps it's an exercise I would like to give you now. Let's do a live exercise. I think it would be very interesting let's think of a parabola. I'll go back to my perhaps to my iPad, sorry. Let's do a test, all of us together, and the one that gets it right, just either share a screen or send me a link, okay? It's not a must, but I think it would be an interesting thing to do. So why don't we do the following? Okay. I really apologize for the speed of technology here. Okay, so we just did the pi a minute ago, and why don't we do something very interesting? Let's see if the LLMs are smart enough to generalize. And let's just draw a parabola. Let's call this 1, this -1, and this 1, and okay. This parabola is obviously something like, I think you all agree, right? Let's try. If x is 0, then we get 1, which is nice. If x is 1 or -1, then we get 0. Now, it would be very interesting for me to calculate the area of this parabola. First of all, does anybody know, can anybody tell me analytically what it would be? It's a simple integral.
It will be x minus x cubed over 3.
Yeah, just put the limits of the integral and tell me what the area, the analytic solution.
Minus half.
No, no. Let's do the calculations. The answer is 2/3, if I remember correctly, but you can try it. Okay, the integral is, of course, x minus x to the third over 3. Put 1 minus 1 in the limits, and we get 2/3. But let's say we don't know it, and we want to calculate it with Monte Carlo method. So again, we can put a square here, and then throw darts. And all we need to do when we get an x, make sure that it's smaller than 1 minus x squared. Okay, so I'm sorry, we do an xy, we do 2 points, xy as before, but we want to make sure that the y point is below the graph. In other words, that it's smaller than 1 minus x squared. So I want to give you a few minutes and just use any LLM you want, get the code in Python, look at it, put it in Google Colab, just do a copy and paste, or even start from Google Colab, and let's see if one of you gets it right. And I'll give you 5 minutes for that. So again, what we need to do is sample points, x and y between 0 and 1. Make sure that the y that we got is below the graph. Count it, do the ratio, and let's see if we get the right number. The one that gets it right, please ask to share a screen. I'm already allowing. And just show us the notebook and the graphs, and I'll be very happy to see someone does it. Someone is able to do it.
Shoki, please share again the iPad.
Sure. And, I would really be happy if someone even goes further and just think about it, telling the LLM to draw a graph of showing how with the number of points that we add, we get asymptotically to 2/3. Again, I'm not asking you to write the code. Just go to your favorite LLM. Believe it or not, my favorite is DeepSeek or Claude. And if you do it with Claude, you can just send the link to me and I'll show it to everyone. But I prefer that we do it in Python and not in JavaScript. So probably a screen sharing would be better.
Like this.
Do we have a winner? I'm sorry, I cannot hear.
Yeah, considering if it's okay, but yeah, I think this is kind of what you're asking for.
So do you have an answer?
Yeah, 2/3. That's what the
Yeah, it's 2/3. But were you able to do it with Monte Carlo?
Yeah, it's Monte Carlo. It's
okay. So can you share your screen?
I'm not sharing. I think I'm sharing.
Sorry. Try now again.
I share again. Wait. Screen.
If you can also be kind and show us the prompt itself.
I see his screen.
You see screen? You see my screen? Okay.
I don't. That's very strange. Hey, Yossi, do you see the screen?
Yes, I can see the screen.
Wow. This is really crazy.
I am not 100% sure that this is the student screen.
Yeah, it is my screen. Like
Okay.
the Monte Carlo integration.
Yes, I can see the screen.
Wow, strangely, I can't.
Do you have an additional screen, Shuki?
No.
No, I don't.
No?
Wait, let's can you do me a favor? Stop sharing and then share again?
Sure. Let's stop. Again. You're seeing it?
Beautiful.
Okay.
Okay, this looks great. Can you please show us the prompt also?
Yeah, it was very dumb. Excuse me. Sorry, I used Claude for that.
Okay.
Like very dumb, prompt.
Beautiful. It's a very good prompt. And can you show us the code? Perhaps go over the code with us and.
Yeah, no, excuse me. Okay. Okay, first of all, you define an area, which is a box. Since this is the, let's call it the X and Y conjunction points. Then within this area, you randomly produce X number of points. Then you define the curve. You define what is under the curve.
Beautiful.
And then you just count.
That's simply beautiful. Was anyone able to also show a graph to show how it asymptotically reaches 2/3 with the number of shots? If someone would share a screen, I'd be happy. Or maybe you can just add another prompt to yours and ask for a graph that shows perhaps even the error as a function of number of shots. Let's try to do it live. Wait, what's your name?
Itamar?
Itamar, hi. So let's just add a prompt. Let's just ask it.
A close, meaning.
Yeah, to show a graph. Just ask it to show a graph as the error is a function of number of shots.
Right. Like, calculation of the random points. Very simple.
Oh, I already see nice numbers there. You see, it's going to try up to 1 million. Beautiful, beautiful.
It doesn't let me copy.
You can just click. There's a copy button. It's play for all to use it. Guys, someone here will need to mute, please.
But do the averaging that takes something that's really anticipated without any competition.
Amazing. Beautiful, just beautiful. Look at that. The error is the number. Very nice. Very nice. So, Itamar, thank you very much. Amazing job. I wanted to add, by the way, that I've been looking at most of the exercises that you've submitted, and I was very, very pleasantly surprised. We have something like 26 people that have submitted, and I think with only three, I found the technical problems not being able to run their code. But the rest have done an amazing job, and the three that I was not able to check their jobs, I will contact them directly and try to understand what the problem was. But I was very pleasantly surprised with the creativity and the level of the work that you've shown. Any questions about Python, programming in general, before we move to the second part, which is linear algebra? Okay. So actually, what we're going to do now is far from a course in linear algebra. It's going to be extremely informal. All I want to do is try to build an intuition for a very important operation called matrix multiplication. We will see that the matrix multiplication will be critical when we do AI. And also it's critical for physics. So before we start, let me share my iPad again. Okay, so we're going to talk a little bit about linear algebra, and let's start with the word linear. Does anybody know why linearity is so important, especially in physics? Maybe before that, we'll explain what linear is. A linear equation has two requirements. One of them is that, sorry. is
We
that
can't
F...
see you.
Oh, you don't have to see me. Do you see the screen?
Yes.
Okay, that's good enough. Let me just... Okay. So what we need for an operation to be linear is that if the operation is working on a sum of two arguments, it should work like that. Now let's show an example where it's not the point. Let's take square root, for example. Okay? Square root of 4 plus square root of 9 is equal to how much? 2 plus 3, 5, right? But square root of 4 plus 9 is the square root of 13. That's not 5. So some operations are linear, some operations are not linear. The reasons linearity is so important in physics and also in AI is because the most important equations are linear. The best example is Schrodinger's equation. And what we'll show in the very near future, that the linear equation allows us to do superposition, which is the heart of quantum mechanics and other sciences. So linearity is very, very important. And what we'll try to do now is define an operation on matrices which will conserve linearity. Okay? And of course, we'll do it all with Python very soon. So first of all, let's talk a little bit about matrices. That's a matrix. That's a matrix. That's a matrix. Let's call this A, B. Let's call this C. Let's do a D. Okay, so I have 4 matrices here. Let's first of all agree on dimensionality. So a dimension of a matrix is a combination of the number of rows and columns. So let's see, how many rows do we have here? We have 1 row, right? We have 1 row and 4 columns. So this one has a dimensionality of 1/4. What about D? It's very simple, right? 2/2. That's D. What about B? How many rows do we have in B? We have 4 rows and 1 column. So this one is B is 4/1. Let's do some more. Guys, for those of you who know linear algebra, I really apologize. But we have to bridge all the gaps here. Let's do another one. Let's do another matrix, sorry. A equals 2, 1, 1, 0, 3, 2. So how many rows do we have here? 3, right? We have 3 rows and 2 columns. Are we all okay? Great. So let's start with the first operation, which is called addition. To add matrices, it's very simple. You just add the components. So for example, let's look at this A and let's look at B, which is 1, 0, 0, 1, 0, 1. If we want to add them, C equals A plus B. Even before we start, we assume that they must have the same dimensions, right? Otherwise, you cannot add all the components. So what we do here is 2, sorry. So it's 2 plus 1. So this one is 3. And then we have 1 plus 0. And then we have 1 plus 0. And 0 plus 1. And then we have 3 plus 0. And 2 plus 1. Okay, so that's A plus B. Very simple, okay? If you want to add two matrices, all you do is just add their components. Another easy one is multiplying a matrix by a scalar. Okay. Multiplication. So that's very simple. Let's say we have a scalar, let's call it x, which is equals to 5, and a matrix A, which is equal to 1, 2, 0, 1. So 5 times A is equal to 5 times 1, which is 5, 5 times 2, which is 10, 5 times 0, which is 0, and 5 times 1, which is 5. Very simple, okay? So adding matrices, just remember they must have the same dimensionality. Multiplying by scalar is very simple. You just multiply each component by the scalar. Okay. So now let's get to the crust of things, and that matrix multiplication. So let's start with something simple. Let's say we have a matrix A and a matrix B. Okay, and we want to multiply them. So I'll start with something very intuitive, and then we'll go a little bit more formal. So the way to multiply is to take, in matrix A, we have two rows, right? We have one row, which is 1, 0, and one of them, which is 1, 2. In matrix B, we have two columns. So in matrix B, I'm looking at the columns. In matrix A, I'm looking at the rows. So in matrix B, we have one column, which is 1 and minus 1, and the other one is 0 and 2. These are the two columns. Okay? So what I do is I multiply a row of A with a column of B. So let's look at the first row. It's 1, 0. And I want to multiply it with the column of B, which is 1 minus 1. So the way I do it is I multiply the 1 with the 1 here and the 0 with the minus 1 here. So we get, and then I add them. So 1 times 1 is 1, 0 times minus 1 is 0, and I add them. So the answer is 1. So this means that, let's do it from the beginning, A times B, which is equal to 1, 0, 1, 2. Again, I apologize for those who know it, because it's really idiotic to see the way I'm showing it now. So if I want to know what the 1, 1 element here, I take this row and multiply it by this column and add the multiplication. So I get, as I said, 1. So let's now try to see what we have here. So what I do here is, again, I take the first column, the first row, and multiply it by the second column. So I get a 0. Let's look now at this point here. So now I take this row, 1, 2, and multiply it by this column. So it's 1 times 1, which is 1, minus 2, and I get here a minus 1. And for the last one, I get this row times this column. So it's 1 times 0, which is 0, plus 4, which is 4. So that's the answer. Now, interestingly, as opposed to addition, when it comes to multiplication, the matrix do not have to have the same dimension. Let me give you an example. Okay, let's take the following matrix. 2, 1, 0, 1, 1, 0. And try to multiply it with 1, 1, 0, 2, 1, 0. Okay, let me just do it nice. Okay, so if we go by the same trick, it should work, right? Because I have a row which has 3 numbers, 2, 0, 1, and a column that has 3 numbers, 1, 1, 0. So let's see. So we get 2 times 1, which is 2, and plus 2 zeros. Okay, let's now go for the second one. So we have this row times this column. Let's multiply together. It's 2 times 2, which is 4, plus 0. So here we get 4. Let's continue now. We have now 1, 1, we have this row times this column. So it's 1 plus 1, it's 2. And lastly, we have this row times this column. So we get 1 times 2 is 2, plus 1 is 3. Okay. So what we saw is something very interesting. The dimension of the first matrix was 2 times 3. The dimension of the second matrix was 3 times 2. And the result was 2 times 2. Now, this is always the case, okay? In order for two matrices to be able to multiply one another, the number of columns in the first one has to be equal to the number of rows in the, the number of columns in the first has to be equal to the number of rows in the second. So you see the 3 and the 3. And the resulting number, the resulting dimensions will always be this, 2, in this case, 2 by 2. So if you want to multiply two matrices together, the first thing you have to make sure is that the number of rows, the number of columns in the first one is equal to the number of rows in the second one. Otherwise, you will not be able to multiply. So you immediately see that if we wanted to multiply them the other way around, it would not work. Okay? So let's go to the most important thing, and this is what happens when you multiply a matrix with what we call a row vector. A row vector is something like this, something we use a lot in physics. Okay. Can someone tell me what is the dimension of this thing? It's 4 over 1, right? Because we have 4 rows and 1 column. This means that I can multiply this thing with anything that has 4 columns. So for example, I can multiply it with a 4 and 4 matrix. Right? But I could also multiply it with 4 over 5. Sorry. No, sorry, my mistake. Let's do it again. Sorry. Okay. So this should work, right? 4 over 4 times 4 over 1. This is equal. And the answer would be 4 over 1. This is really, really important, critical. So what we see now is that if we take a matrix and multiply it by a vector, we always get a vector. Is this understood? It's critical, critical, critical. And I think you can understand that this is the relationship to science in general. Because what is a vector? A vector is a list of numbers. It could be a position of a particle, the distribution of a particle. It could be the height, weight, and IQ of a person. And what a matrix does is change this vector because it transfers it to another vector. So when you multiply a matrix by a vector, you get a new vector. This means that the change is always in the matrix. Okay, we'll see. I will give you a very nice exercise where you will be able to see how classical and quantum mechanics become almost one when you understand this concept. Okay, a matrix is an operation. Think of it as an operation on a vector, something that changes a vector to another vector. So before we go to something which is more scientific, I want to show a very fun example of the philosophy of thinking of matrices as something that produces operation. Okay, so let's look at a polynomial. Polynomial, we all know what polynomials are. Let's look at this one, for example. 2 times x to the third plus 1 times x to the plus 7. Okay? Can anybody think of an idea of how I can look at this polynomial, as how I can represent this polynomial as a vector? Let's think, look at this polynomial or any polynomial, and let's try to think of a clever way to represent it as a vector.
Maybe 2107.
Beautiful, beautiful. So let's look at the vector for a minute. And I will do it a little bit differently. Do you agree? Does it make sense? Okay, let's do another polynomial. What about this polynomial? Sorry. What about this polynomial? It's a polynomial, right? That would be very simple. It would be just 5, 0, 0, 0, because we don't have other. What about this polynomial? It's also a polynomial, right? So let's see. We have 0, 0, 1, 0, 0. And lastly, help me with this one. 5x to the fourth plus 2x squared plus 7x minus 1.
Minus 17025.
Very good. Minus 1, because we have minus 1 x to the power of 0. Then we have 7. Then we have 0 because we don't have x squared, right? Then we have 2, and then we have 5. Beautiful. What we'll do very soon is something beautiful. We'll try to make the derivative of a polynomial. So let's look at this polynomial for a minute and help me derive it. Make a first derivative. So it's easy, right? It's 20 x to the third plus 6 x squared plus 7. Am I right?
20, Shuki.
Sorry?
20. You forgot the 0.
Oh, I'm sorry, 20. Okay, so this can also be looked at as a vector, right? 7 is here. The 7 went And then we have 0. So we have 0. And then we have 6. And then we have 20. Do you agree with me? So look, something very interesting happened here. We had a representation of a vector, then we derived it, and we got another vector. Now, it would be interesting to think of a matrix that would represent the first derivative. Do you agree with me? So let's do it together, and let's do some Python. What I want to show you is I want you to always identify a matrix as an operation which changes a vector. That's what we do a lot in physics, and that's what we're going to do in our exercise, which I will provide you with probably in the next lesson. So let's do a little bit programming. Okay, and what I'll do here is I'll show you a lesson that I prepared for you in linear algebra, but don't worry, we are going to do the derivative of the polynomial very soon. Okay. So what you see here is, I think it was Claude or I don't, maybe ChatGPT. I asked it to provide a quick lesson to my students in linear algebra. Actually, I think it was ChatGPT. Yes. So I will send you the chat, the link later, but what you can see is I asked it to provide a tutorial for beginners.
Shuki,
And
please share the screen.
yes, sure I will. Okay, do you see my screen?
Yes.
Yes.
I don't see it. Let's do it again. Sorry. Okay, great. So what you see here is the thread I did. I think it was with, yes, ChatGPT. Let's see a few interesting things. Here I asked it to teach us a little bit about matrix multiplications, and it gave a very nice example. And here I asked it to show linearity, to prove that matrix multiplication is linear. If you remember, we started with this. And many people ask me, how did people get this crazy idea of multiplying matrices in the way that you showed us? The rows times the columns. And the answer is very simple. That's probably the only way to define multiplication, which is linear. So had we tried a different idea of multiplying matrices, it would not be linear. But when we do it this way, it is linear. And look at this nice example. So we have a matrix A, a matrix B, and now we're adding them. A plus B is equal to this matrix. Okay? And now let's show that it's linear. Sorry, this is the multiplication of A and B. You see that they will be able to multiply because they have 2 and 2. And let's show to the proof. Let's go to the proof of linearity. Okay. So what you see here is a proof of linearity. This is one matrix. It's a vector actually, but a vector is a matrix. This is another one. And this is a matrix. So what we're doing first is adding x and y, which is 3, 3, and then multiplying it by a, and we're getting 3, 9. Okay, so a times x plus y is 3, 9, this vector. And now to prove linearity, we're trying to see if it will be equal to ax plus ay. And you see it here, and we're getting the right answer. Now, there is another thing about linearity which I didn't mention, which is called homogeneity. And another requirement of linearity is that if you have an operation of a scalar times a matrix, it will be equal to the scalar times the matrix. It's very intuitive, so it will not surprise us. But as you can see here, you can see the proof again. Okay, so now we know that the way we defined matrix multiplication conserves linearity. Okay, it's critical to understand the reason we went to this wild idea of multiplying matrices in the way I showed is because it conserves linearity. And here I asked it to provide a formal proof, not just by an example. So it provides a beautiful proof to show why it's linear. Really, really nice. And here I even asked it to be more formal. So it gave me an even more formal proof. Okay. And I think it's time for us to go to the polynomis. 1 minute. Just give me a second. Okay. Okay. So if you remember, we found a very interesting way to represent a polynomial. And as a vector. And since deriving a polynomial gives us another polynomial, another vector, we're looking for a matrix that will actually do the job for us. Okay? So, sorry. Hallelujah. So what you see here is the definition of the polynomial that will derive this vector. Okay? I will, if you want, in 1 second, I will demonstrate it. See here, it defined the polynomial 1, 2x plus 3x squared. This is how the polynomial would look. This is the derivative matrix. And if we multiply this matrix by this vector, we should get the right answer. In other words, the derivative. Okay, so let's see. So this is the matrix. This is the original vector. And this is the matrix. Now, I already see that there's a very good chance that this is the true answer because I get a 0 here. You know, when we derive a polynomial, we always get one lower power of the polynomial. So, and another thing we see is that the 2 comes all the way to the top. And that's also true, right? Because if we have 2 times x to the power of 1, the 2 will go all the way to the top. Now, what happens if you multiply this matrix by this vector, you will get this vector. What happens if you do it again? You'll get the third derivative, right? So actually what I asked it to do is create a new matrix, which is a multiplication of the 2 matrices. And this is the matrix. And the beautiful thing is that this matrix is actually a second derivative matrix. So any polynomial that I multiply with this matrix now will get the second derivative. And if I multiply it again, I will get the third derivative. And you can already see that if I multiply it one more time, it will get 0. And that makes sense because there's a limit to how many times you can derive a polynomial. So basically, that's what I wanted to show. And may we do a 3-minute recess and then continue for another 15 minutes to do something which is really important, which is called eigenvalues and eigenvectors. Okay, so I need 5 minutes recess. Okay, so I'm ready if you are. And we will lastly go into probably the most important thing you will learn today. And this is the notion of eigenvectors and eigenvalues. But before that, let's first of all, from now on, limit ourselves to two-dimensional matrices and vectors. Okay, so this would be, for example, a vector, 1, 3, and this could be a matrix, 1, 0, -1, 1, for example. So let's agree now that since everything is going to be two-dimensional and we're going to talk about real numbers, it means that we can represent the 1, 3 graphically on an XY axis, right? So how would Y look? It's 1 here and 3 here. So I would say that Y would look like something like this. Okay? So every two numbers we can actually draw on this plane. Now, as we know, if we multiply A times Y, we're going to have another vector. Because A is 2 times 2, and Y is 2 times 1, two-dimensionality on 1. So we're going to have another two-dimensional vector. Actually, let's do the multiplications. So it's 1 times 1. Again, it's this row times this column. And then we have this one, which is -1 plus 3, which is 2. Am I right? Let's do it from the beginning. 1 times 1, so it's 1. Okay, so the answer is 1, 2, which means that the new vector is going to be this one. So what this matrix did is actually two things. It rotated the vector and it changed its length. Am I correct? And obviously, that's the general thing that would happen when you take a vector of two components and multiply it by a matrix. The most general thing that can happen is that it would change its length and change its angle. Nothing else can happen. Of course, there is a situation where nothing will happen at all. If we multiply it by an important matrix, which is called the unit matrix, which has ones in the diagonal, then if we multiply this, then we'll get the same thing. But that's a boring matrix. Now, there's one kind of matrix which is very interesting, and that's the one that would only rotate the vector. Okay, these are called rotation matrices, and we will come to them in a second. So a rotation matrix will conserve the length of the vector. Unfortunately, maybe we'll have time for me to prove orthogonality and explain why it conserves the length. We'll see how time goes. Otherwise, you just have to believe me that there is a family of matrices which are called the rotation matrices, which simply will rotate the vector. But there's another thing which is even more interesting, and it's the following. So imagine that we have a certain vector, a certain matrix, excuse me. Let's say A equals 2, 1, 1, 0. And an interesting question is, I already know that every vector that I will draw here will be changed by this matrix by definition, right? It will either, stay the same or something will happen to it. But the interesting question is the follows. For this matrix, is there a certain vector that if I multiply the matrix with this vector, it would not rotate at all? It would maybe change its length, but it will stay in the same direction. So maybe from this, it will go to something like this, or even something like this. This is just multiplying it by -1. So the interesting question is as follows. If I have a matrix, can I find a vector a special vector that if multiplied by this matrix, it will not rotate. It will just be multiplied by a certain factor. And maybe to explain a little bit more, so let's say we have a vector, let's call it y, which is 1, 3. And you already remember that if we multiply by a scalar, what happens is that we multiply each component. So this becomes 4, 12. But this is the same direction. It's the same vector, only a different length. So if I draw 1, 3 here, this vector, and if I draw 4, 12, it will be the same direction, but a different length. So the interesting question is there a matrix? Is there a vector for a specific matrix that if I multiply this vector by this matrix, it will not rotate. It will stay in the same direction. It may change its length. And the answer is yes. And unfortunately, I will not be able to prove it to you. But if the matrix is symmetric, and symmetric means something like this. This is a symmetric matrix. Okay. This is not a symmetric matrix because 2, 1 is different from 1, 2. This one is symmetric. So we don't care about the diagonal at all. We just care about the two other elements. And if they are equal, like here, then the matrix is symmetric. And there's a beautiful proof. And again, if we have time, I'll be happy to show it to you. It's very simple. That shows that if a matrix is symmetric, yes, you will have not only one vector, but two different vectors. I'm generalizing a little bit, okay? But in general, if you have a symmetric matrix, if it's 2 on 2, you will have two special vectors. They are called eigenvectors, in Hebrew, vector atzmi. So for every symmetric matrix, you will have the number of vectors which is equal to its dimensionality. So if it's a 2 on 2 symmetric matrix, you will get two special vectors that do not change when you multiply them by this matrix. Okay, if you have a 4 on 4 matrix, you will have 4 vectors like that do not change if you multiply by this matrix, assuming this 4 on 4 matrix is symmetric. Okay, I'm not saying that if it's not symmetric, it will not have eigenvectors. That's not what I'm saying. Okay, what I'm saying is that if it is symmetric, it will have 4 vectors which are orthogonal, and they are multiplied by real numbers. The number that we multiply is like this 4 here. It's the number that changes the length. So if I want to write what I just said in a little bit more formal way, I would write it like this. If I have a matrix A, and I multiply it by a vector X, and the result will be a number. Lambda is a number, 5, 2, minus 1, a real number, times the same X. Then this is called the eigenvalue, and this is called the eigenvector. And we're going to demonstrate everything, don't worry. But just to summarize before we go to Python, we decided that we're going two-dimensional. We're going to be very flat people from now on. By the way, all the lesson that we're going to have on quantum mechanics is going to be on a 2-level system. Okay, so we're just looking at a very simple plane of linear algebra, which is the 2-dimensional plane. And what we understand is that each vector can be presented as a drawing on a 2-dimensional plane. We said that the matrix will just a multiplication by any matrix will change this vector. The most general change is to its length and it's to its angle. And then we talked about two unique situations. The first situation is a rotation matrix. In other words, the matrix only rotates the vector. It conserves its length, but changes its angle. And the second special situation is we said that every matrix, if it's symmetric, will have two directions, two vectors that do not change if we multiply this matrix by this vector by this matrix. So maybe we'll start with some interesting questions to all of you. And my first question, let's say we have a rotation matrix. Do you think that this matrix should have an eigenvector? So let's say we have a two-dimensional rotation matrix. It's a matrix that rotates a vector. And the interesting question, of course, you will agree with me that the rotation matrix depends on an angle, right? You can rotate a vector by 20 degrees, by 45 degrees, by 180 degrees. And my question, is there a certain angle? Maybe let's ask it differently. Let's say we have a rotation matrix of 45 degrees. In other words, this matrix will rotate our vector in 45 degrees. Does this matrix have an eigenvector? In other words, is there an eigenvector in the world that if I rotated it by 45%, it will be the same? Of course not. Of course, because you're rotating it, it cannot be in the same direction. It's a contradiction. But if you rotate a vector by 180 degrees, for example, then think about it. It was like this, and now it's like this. So it's in the same direction, just multiplied by -1. Do you agree with me? Okay, so let's see what Elon Musk has to say about it and go to some grok stuff I did with matrices. Okay. So I asked Grok to show me an example of a rotation matrix, and this is how a rotation matrix look for a specific angle. Okay, so if we had 45% here, what you see immediately that it's not a symmetric matrix. If I put 45%, then it's not symmetric, right? Because a sign of, here we have a minus square root 2/2, and here we have a plus. So for 45 degrees, this matrix is not symmetric. So I should not be surprised that it doesn't have an eigenvector, right? Because I said I promised you, if the matrix is symmetric, you'll get eigenvectors. By the way, I'm a little bit generalizing, but please forgive me. It's something that sometimes, there's something which is called degeneracy. I don't want to get into it. But in general, if you have a 2/2 matrix that is symmetric, you will get two directions that are not changed. So first of all, we understand that in the specific situation where we have 45 degrees, this matrix is not symmetric. And as our logic tells us, of course, how can it have an eigenvector? If this matrix rotates every vector by 45 degrees, it will not have an eigenvector because it changes the vector. An eigenvector is a situation where the vector doesn't change the angle, it only changes the length. Fantastic. Now, if I put 180 degrees here, that's different. We get 0 here and 0 here. Voila, that's a symmetric matrix, right? If we have 0 here and 0 here, the matrix is symmetric, so I'm not surprised that it has eigenvectors. Actually, every vector is going to be an eigenvector in this situation. So just to summarize, we talked specifically about the rotation matrix. We explained that a rotation matrix, by definition, you can see here, if this is the original vector xy, this will be the vector after rotation. And if you can see by simple trigonometry, it's just taking a vector and rotating it by an angle of theta. And of course, for 0 degree, by the way, 0 degree is also there's an eigenvector because you're not changing the vector. So it should also work. That's for pi/4 for 45 degree. You see it's not symmetric, so we're not going to have an eigenvector. And now let's go to the more interesting stuff, which is discussing specifically eigenvectors. Okay. So what you see here, is a specific matrix which he started to work with. Let's look for it. That's the matrix. 2, 1, 1, 2. Is it symmetric? Yes. So for sure, there's a very good chance that we'll have very nice 2 eigenvectors for this matrix and 2 eigenvalues. So this is the way to calculate it. Again, it's very simple. I will not go into it. It's a simple square equation. And what you can see here is that there are 2 vectors. This is the first vector, which is an eigenvector. And this is the second one. So these 2 vectors are eigenvectors. And this means that if you multiply the matrix by these vectors, they will stay in the same angle. Okay? Okay. So now I asked it to do something more interesting. And I asked, let me look for the prompt here. Please create a Python code which gets 2 input numbers from the user. So now I want the user, us, to input 2 numbers. And these 2 numbers will be the components of any vector, right? And what I want the program to do is to show the vector, display it on a 2-dimensional plane, but then also multiply it by this matrix. And I'm reminding you the matrix is this one. Maybe you want to write it down. That's the matrix we're talking about. 2, 1, 1, 2. It's a symmetric matrix. These are the 2 eigenvectors. By the way, can someone tell me quickly what happens to this vector when we multiply it by this matrix? What happens to it? It has to stay in the same direction because it's an eigenvector, but does it grow? Does it shrink?
It is multiplied by 3.
Exactly. So if you multiply this matrix by this eigenvector, we'll get a vector which is 3, 3, which means that we took the original eigenvector and multiplied it by 3. So the eigenvalue here is 3. Does anybody know what happens when we multiply this eigenvector?
Change direction.
But what happens to its size? Stays the same, right? See, let's look for the calculation of the eigenvalues. 1 minute. So you see 1 eigenvalue is 1, which means that really nothing happened to it. Okay, you multiply it by 1. The other one is multiplied by 3, as it was said. And as I said, it's a simple square equation, and these are the 2 numbers that we got, 1 and 3. So let's now go to the Python program that I asked Grok to do. And what I asked it to do is something very simple. Just let me enter some vectors and tell me what happens to these vectors when I multiply them by this matrix. Okay, so let's go here and just run the software. Run the program that Grok gave us. So now I'm being asked by the program to enter 2 numbers. So let's do something interesting. Let's start with 1 and 1. What do you think will happen? Beautiful. You see, this is 1 and 1. And the blue one is 1 on 1, and the red is after I multiply by the matrix. But you remember that the matrix simply multiplied it by 3. So I'm not surprised at all. Let's do a different vector now. Let's do 0 and 1. Sorry. Give me a second. Okay, let's do now 0 and 1. 0 and 1. Okay, so 0 and 1, we're not surprised. And this is what happens when you multiply. So you see that the blue arrow is not an eigenvector, right? Because what happened to it? Not only did it change its length, it even changed its direction. Let's try another one. Let's try -5 and 5. What do you think will happen? I am reminding you, remember -1 and 1 was an eigenvector. So here, the same thing happened. It didn't change at all. -5 and 5 is like 5 times -1 and 1. So we shouldn't be surprised. And just lastly, let's do one more example. Let's do 1 and 1. No, 1 and 1 we did, I think. Let's do 1 and 0. Okay, so this is 1 and 0, and this is the matrix time this vector. So what we saw here is a very nice example of a matrix 2, 1, 2, 1, 2, 1, 1, 2, which had only two directions that it would conserve. 1, 1, and 1 minus 1. And by the way, it's not a coincidence that these two directions actually are orthogonal, have a 90-degree angle. You will always see it when you have real matrices 2 over 2 symmetric. The eigenvectors will always be orthogonal to each other. They have a 90-degree with each other. Maybe with your permission, I will end with one more example and ask you, okay, what will happen if I go with -2 and -2? I am reminding you that 1, 1 was an eigenvector. Remember that 1 over 1. Now, -2 is simply -2 times 1 over times 1, 1. All we do is just multiply it by 3 because that was the eigenvalue. So again, you see that everything that is on this axis and this axis will not change by this matrix. This matrix will only change length. It will not change directions. And again, please understand, these two eigenvectors and eigenvalues were only related to the specific matrix, 2, 1, 1, 2. If we change this matrix, let's do it. Let's change it. Sorry, let's look for it. How about we change it to, let's just put a 1 here. Right? It will still be symmetric. Let's see what happens. Beautiful. Now 1, 1 is not an eigenvector anymore because we changed the matrix. You see, 1, 1 before would be multiplied by 3. But now I changed the matrix, so it has different eigenvectors, and eigenvalues, which can be very easily calculated. So to summarize, what we've learned is that if you have a square matrix, which is real and symmetric, it will have two dimensions, two directions, or two eigenvectors, which will be indifferent to this matrix by multiplication. If you multiply one of these eigenvectors by the matrix, it will be indifferent. It will maybe change in length, but who cares? It will not change in direction. That's the most important thing. Okay? Any questions? If you want, I can explain the calculation, but it's really, really very trivial.
Is there something the same with the 3-dimension vector and 3-on-3 matrix?
Of course. Everything is exactly the same. First of all, you have 3 Actually, if you want, we can do it as we speak as an exercise. Absolutely. If you have a 3-dimensional matrix which is symmetric, it will have 3 eigenvectors, and these eigenvectors will be orthogonal. They will be right angles to each other. It's very deep and important. Are you a physics student?
No, biologist.
Oh, right. I remember. You asked me about
But I have learned computer science for my first degree, so
I understand. Okay, so you should know. So if we talked in 3 dimensions, everything is the same. If the matrix would be symmetric in 3 dimensions, it will have 3 eigenvectors and 3 eigenvalues. The eigenvalues will be real. The eigenvectors will be orthogonal to each other. In other words, in 9 degree. If you think about it, what it really does, it sort of rotates the axis because they're still in 90 degrees. Now, you also have, obviously, a rotation matrix in 3 dimensions. Obviously, you can take this and change it in 3 different dimensions. It will not be a symmetric matrix for the reason that I explained. It by definition cannot be symmetric because if it's symmetric, it would mean that there are angles, like I showed with the 45 degrees, that will not change. And obviously, that doesn't happen with every angle. So a rotation matrix in 3D is not symmetric. But please just go to Grok or DeepSeek and ask it to show you a 3-dimensional matrix, a rotation matrix. Ask it to rotate it, to do some examples of rotations. Everything I said in 2D is exactly the same in 3D and also in 4D, but 4D we cannot obviously imagine it. Okay, so what we've learned today is really critical to understand AI. And the part about the matrix acting as something that changes a vector, an operator, as I showed with the polynomial derivative or the rotation matrix, is going to be very important for the exercise that I probably will give next lesson, because there we will talk about, believe it or not, a random walker that changes from time t to time t plus 1 by a matrix. So believe it or not, but we can take a 1-dimensional random walker and understand how time evolves from time t to time t plus 1 to t plus 1,000 by simply doing matrix multiplication. It's a beautiful exercise that will also be an introduction to quantum mechanics, and we will discuss it probably in the next lesson. Any questions now?
Yeah, I wanted to ask about the vectors we multiplied, which weren't כאילו הווקטור עצמי. So we saw that the vectors somehow rotated to the direction of the vector עצמי, but they כאילו it was המקרה or it's general.
So let me try to explain. Let's say that this is a vector, okay?
Okay.
If this is and let's say I have a matrix, okay? The matrix will act on this vector. If this vector is an eigenvector of the matrix, it will be in the same direction. Maybe it will be shorter, maybe it will go the other way around, but it will have the same direction, okay?
Yeah.
And eigenvector doesn't change its angles or its direction as a result of multiplication by a matrix. Is this clear? This part? Okay, now if this vector is not an eigenvector, then everything can happen. Then it could change in size, it could change in angle, then anything can happen.
But in the examples you showed with the code, it changed to the direction of the eigenvector. So I just asked if it's kilo.
Let's with your permission, let's just do it. Let's run the code together and try to explain what the problem is. But let me just return to the original matrix. I think it was 2 here, right? Okay. So what I'll ask you to do is just ask for a vector. What vector would you like to see? Give me components that you would like me to enter.
Minus half and half. And the quarter.
And the quarter?
Yeah.
Okay. So first of all, you already agree with me that it's not an eigenvector, right?
Yeah.
Okay, so it has to change. Let's see. You see? Beautiful. That's the vector that you asked for, and that's the result. If you want, we can multiply together the matrix, and I'll show you that it will be something like, I don't know, 0.6 and 0. Why the y will be 0? Do you want us to do the multiplication together? And you'll see. Just take the matrix that I showed, 2, 1, 1, 2, multiply it by what you just gave me, which is minus half and a quarter, and you will get this thing.
Okay.
Okay?
Yeah. Thank you.
Very good. Any other questions, please? Okay. Have a great day. We'll see you in person next Tuesday. Bye.
Thank you.
Thank you. תודה רבה, שוקי.
Thank you.